Hi, my name is Brian Caffa. I'm in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health, and this is Mathematical Biostatistics Bootcamp, Lecture 3 on Expectations. Expected values are ways of summarizing probability distributions in the same way last lecture we talked about quantiles to summarize probability distributions. So we'll talk about the rules that expected values have to follow. We'll talk about the basic mechanics of how you calculate expected values for discrete random variables and continuous random variables. And we'll talk about important subclasses of expected values, the mean, variances, and we'll talk about how to interpret variances because they're a little bit trickier with Chebyshev's inequality. The expected value or mean of a random variable is the center of its distribution. It's in essence a particular definition of the middle of a distribution. There's more than one definition of the middle of a distribution. For example, the median would constitute a different definition of the middle of a distribution. But the mean is a particular one, and we'll talk about the intuition behind it in a minute. And consider how you would calculate the mean for an example for a discrete random variable. We denote the mean with this capital E here, which stands for expected value. And then usually, for whatever the reason, we tend to use square brackets for expected values rather than parentheses. And so we might write expected value of X. Here, again, we're using a capital X because we're talking about a conceptual value of the random variable. This, in the case of a discrete random variable, is the sum over all possible values that X can take of X times P of X. Now note here, if we didn't have this X out in front of the P of X, this would just sum to 1 because the PMF sums to 1 by the definition of a PMF. So this X out in front is what turns it into an expected value. Here we're just talking about the expected value of X, but if we wanted the expected value of X squared, it would be the sum over X, and we would have a little square in front of the X right here that we're summing over. So sum over X squared times P of X. E of X, one way to think about expected value of X is that it represents the center of mass. If the X's are locations and the P of X's are weights. And I have kind of a schematic here on the next slide that shows an example. So imagine if on the horizontal lines here, let's suppose the leftmost line is at the point 0, and it's just a real line extending in the positive direction. And each location of a line here is the value that X would take. So in this case, X takes 4 possible values, 2 low values and 2 high values. And the height of the bars is P of X. So in this case, P of X is equal for each of the 4 bars. So because P of X is a probability mass function, each of these 4 bars would have to take value 1/4. So the expected value then would be the center of this distribution, the point at which you would balance this out if this was, say, for example, 4 little bars and you wanted to put your finger on the horizontal bar so that it would balance out. And here, of course, because the bars are all the same height and you have 2 on the left side and 2 on the right side placed in the same configuration, the geometric center of mass would be right in the middle. Well, what would happen, consider the one next to the right, what would happen if you had 3 all squashed up on the right-hand side and 1 really far on the left-hand side? Well, the one really far on the left-hand side would pull the mean away from the center of the 3 just to a little bit outside of it. And then I go through 2 other cases over here where I vary the heights of the bars and their configuration. In each of these cases, the fulcrum point at the bottom is exactly where you'd have to put it to balance out the bars. And that's where the expectation gets its definition from. It actually draws exactly from the physics definition of center of mass. And in this case, it's exactly just another property of a probability mass function in order to characterize it. Let's talk about how you calculate the expected value for a coin flip. So in a coin flip, our sample space is heads or tails, and we'll define our random variable as being 0 for tails and 1 for heads. let's calculate the expected value for the probability mass function from a fair coin. That is, it's a 50% chance of tails and a 50% chance of heads. So let's plug directly into the formula. The expected value of the coin flip X is 50% 0.5 probability of a tail times the value we've assigned for a tail, 0, plus 0.5 times the value we've assigned for a head, 1. Add those up and you get 0.5. So the expected value of a coin flip is 0.5. This exactly makes sense if you think back to our previous page. If you had a bar at 0 and a bar at 1 and they were both equal height, you would put your finger right at the 0.5 to balance out that bar. So it maps intuition. Also note, the expected value does not have to be a value that the random variable can take. In this case, the random variable can only take values 0 or 1, but the expected value is 0.5, which is between the two. Okay, let's go through the same exercise, but now instead of a coin, let's talk about a die. Here, the possible values that the die can take are 1, 2, 3, 4, 5, and 6. We're going to assume that the die is fair. So all of the numbers have probability 1/6 of occurring. What's the expected value of that die roll? So we denote the expected value again by E bracket X. Here we have 1 times the probability of getting a 1, 1/6, plus 2 times the probability of getting a 2, 1/6, and so on. And if you add them all up, you get 3.5. Again, this makes perfect sense. You have 6 bars of equal height, 1 at position 1, 1 at position 2, 1 at position 3, 1 at position 4, 1 at position 5, and 1 at position 6. And of course, if you were to balance that out with your finger, you'd put it right in the middle of those numbers as 3.5. That covers discrete random variables, at least 2 examples of discrete random variables. Let's talk about how you do continuous random variables. Well, again, the definition follows exactly from the physical definition of center of mass. And in this case, the expected value of a random variable x is the integral from minus infinity to plus infinity of t f of t dt. And here, t is just the dummy variable of integration. So it's pretty much the same formula. Here, if you omit this value t right here, then the integral just works out to be 1 again, because f is a probability density function. So it's putting the t there that turns it into expected value. If you wanted the expected value of x squared, then it would be integral minus infinity to plus infinity t squared f of t dt. And this just borrows from the definition of center of mass for a continuous body rather than the center of mass of a group of discrete bodies, exactly from physics. And again, it's just a description, or it's a useful summary of the density function f, which is a complicated functional construct. It reduces it down to one number, which is a property, which is what we kind of think of this as at least one of the definitions of the center of the density f. Let's go through an example of calculating the expected value of a particular kind of random variable, one that we have not encountered before. So let's think of a very simple density. The density is such that it's 0 below 0, constant at the value of 1 between 0 and 1, and it's 0 above the value 1. So let's mentally, just real quick, verify that this is in fact a valid density. Well, this density is exactly a brick, starting at 0, ending at 1, with height 1. You don't even need calculus to verify that this integrates to 1, because it's just a square. Its area is the length of the base, which is 1, times the length of the height, which is 1. 1 times 1 is 1, so it's a proper density. It's also positive everywhere because it's 0 below 0, 0 above 1, and the value 1 between 0 and 1, so it's positive everywhere, so it's a valid density. This is, in fact, actually an extremely important density. It's a pretty simple one, but it's an extremely important density, and it's called the standard uniform density. It sort of represents the idea that any value between 0 and 1 is equally likely. So imagine if you were to drop a pencil on a line between 0 and 1, and you were dropping that pencil in such a way that it was equally probable to land anywhere between 0 and 1. This density would represent that process. Well, let's go ahead and calculate its expected value. Now again, we already know what the answer is from the geometric argument. It's a brick that starts at 0 and ends at 1. The answer has to be 0.5 because if you wanted to balance that brick out, you would have to put your finger right in the middle. So let's just verify that calculation. Here, our expected value of our uniform random variable x is the integral from 0 to 1. And again, we have x, right? In the previous slide, I had t, but let's just use x in this slide, times the density, which in this case is just the constant 1. So I just didn't write it down. Then dx, the variable of integration. And so that integral is x squared over 2, evaluated the bounds 0 to 1, which works out to be 1/2, exactly what we would have thought. Incidentally, I just want to remind everyone of this notation. The capital X in the expected value represents a conceptual value of the random variable, whereas the little x in this equation represents the dummy variable of integration, a value that's actually getting numbers plugged into it. So it wouldn't have mattered for this little x if we had used x or t or z or w or whatever. However, it's important that we kept it at capital X. That's what we've assigned this random variable, the value capital X. So it's a small point, but keep that in mind. So I wanted to talk about something that always comes up in my in-person classes when I talk about this. So here we calculated expected value of x. And I told you that expected value of x squared, well, you would just calculate integral from 0 to 1, x squared dx. And a question that always comes up in class is, well, wait a minute. I could calculate expected value of x squared that way, or I could figure out what the distribution of the square of a uniform actually is, right? A uniform random variable is a random variable representing some process. So the square of that has to be a random variable, and it itself must have a density. So I should be able to calculate the expected value from that density, and it should be the expected value of y. Let's say if y is x squared. Do I get a different answer if I figure out what the density associated with the square of a uniform random variable is? Do I get a different answer if I calculate the expected value that way, or if I calculate the expected value this way by just putting a square into the expected value calculation from the original uniform density? At any rate, you'll be happy to know that you get exactly the same answer. And in fact, I would also add that it's a lot easier to just put the square in this integral equation because we automatically know off the top of our head what the density of a uniform random variable is. We may or may not know what the square of a uniform random variable is. So this should give you some basic examples of calculating discrete and continuous expected values. In the problems, you'll have both harder and easier examples to work out, and in the assessment, we'll have harder ones. In the next section, we'll talk about rules that expected values have to take. So previously, we talked about expected values and their properties and a little bit of how to calculate them. Now let's talk about the expected value operator itself. And the expected value operator is in fact a linear operator, and that'll greatly simplify calculating expected values for some relatively complicated things. So let me assume that A and B are not random numbers. So when you think about A and B, think A is something like 5. It's this number that you can plug in. And X and Y are actually two random variables. Then expected value of AX plus B works out to be A expected value of X plus B, exactly what you'd hope it to work out to be. And expected value of X plus Y works out to be expected value of X plus the expected value of Y. And the reason it works out in these cases is because the expected value is a linear operator. It is not always the case that expected value of g of x is equal to g of expected value of x, where g is some general function that's not linear. This can happen with specific random variables and specific values of g, but in general, it's not the case. The most sort of famous example where it's not the case is that expected value of x squared is not equal to expected value of x whole thing quantity squared. Now let's talk about what the difference of these two entities is. What do we mean by the difference between these two things? Here, x is a random variable. X squared is the random variable you obtain by squaring x. So, for example, if x is a die roll, it can take values 1, 2, 3, 4, 5, 6. X squared then can take the values 1, 4, 9, and it takes those values with probability 1, 6 each. So the expected value of x squared represents the expected value of the squared random variable. On the other hand, expected value of x quantity squared represents what you obtain if you first calculate the expected value of x and then square the result. And these two things are not equal. This is a well-known example where expected value of g of x is not equal to g of expected value of x, and we'll see in a couple of slides why it is a well-known example of that property. But in general, I would like you to remember that if g is not a linear function, then you can't just commute expected values outside of g to the inside of g. And that rule will generally hold. If it's linear, if g is a linear function, then you can always do it. If g is not linear, just in general think that you cannot do it. The expected value rules hold no matter what constitutes x and y. X could be discrete, continuous, mixed, discrete and continuous. Y could be discrete, continuous and mixed, and the rule still holds. So let me go through an example. Suppose you flip a coin x, and as we normally do, x is 0 if it's tails and 1 if it's heads, and you simulate a uniform random number y. The random number is between 0 and 1. What's the expected value of their sum? Well, the sum of a coin flip and a uniform random variable is a weird distribution. It's not obvious, especially if all you've had is the handful of lectures from this class, how you would calculate that distribution. And then from that distribution, then calculate the expected value. However, we do know how to calculate the expected value of a uniform random variable and the expected value of a coin flip. And so the expected value of their sum is the sum of their expected values. We know the expected value of the coin flip is 0.5. We know that the expected value of the uniform random variable is 0.5. So that expected value is 1. So you can see how these expected value operator rules make calculating things associated with expected values a lot easier. Another example is suppose you roll a die twice. What is the expected value of the average of 2 die rolls? So you often roll 2 dice when you're playing a board game, for example. Okay, let's let x1 be the result of the first die and x2 be the result of the second die. Now, the variable that we're interested in, let's call it y, equal to x1 plus x2 divided by 2. Now, one way you could calculate the expected value of y is to figure out what the distribution was of the average of 2 die rolls. So let me give you a sense of this really quickly. The reason we think the distribution of a single die roll is 1/6 at each number is if you roll a die a lot of times, you get about 1/6 of the die rolls are 1, 1/6 are 2, 1/6 are 3, 1/6 are 4, and so on. And then kind of geometrically, we're modeling the process as if they're all equally likely. And so that's why we're going to model the population of die rolls as having probability 1/6 on each number. Now, this implies a distribution on the average of 2 die rolls, right? The smallest number it could take is 1, right? 1 plus 1 divided by 2, the average of if you were to get 2 1s. And the largest it could take is 6 plus 6 divided by 2, or 6, if you were to roll 2 6s. But it takes different values in between, and it's not equally likely for all the numbers in between. A 1 has probability 1/36, but some of the middle values have higher probabilities. So this, at any rate, our variable y itself has a distribution, and you could get a pretty good sense of it. Maybe you could do this by taking 2 dice, rolling them, taking the average, rolling them again, taking the average, doing that over and over and over again, and plotting, a bar plot of the frequency of the averages that you get. And that would give you a good sense of what the population distribution is, or you could work it out on pen and paper as to what the distribution actually is. And then once you get that worked out, then you could use your expected value formula to calculate the expected value of y directly by doing summation over all the possible values of y times p of y and calculate its expected value. Another way to do it is to directly use the expected value as a linear operator rules. So in this case, expected value of x1 plus x2 divided by 2 is 1/2 expected value of x1 plus the expected value of x2, because the 1/2 is a non-random variable that we can just pull out, and the expected value goes across the two sums here to get expected value of x1 plus the expected value of x2. That then yields 3.5 plus 3.5 divided by 2, which is 3.5. Now you might be wondering after hearing this is, oh, that's interesting. The expected value of the average of two die rolls is the exact same as the expected value of an individual die roll. And that is exactly the case, but you're probably thinking, maybe does this extend beyond that? Is the expected value of the average of n die rolls equal to the 3.5 as well? And the answer is yes, that's exactly true. In fact, that's a nice segue into our next slide, where we actually derive the property that we were hinting at in the previous slide, namely that the expected value of the average of a collection of random variables from the same distribution is the same as the expected value of the individual random variables. So let's let xi for I equal 1 to n be a collection of random variables, each from a distribution with mean mu. Just want to also point out that we tend to use Greek letters to represent population quantities. In this case, the population mean of the distribution is mu. So let's calculate the expected value of the sample average of the xi. Well, we want the expected value of the sample average, which is 1 over n, summation I equals 1 to n to the xi's. The 1 over n pulls out because it's not random. The expected value commutes across the sum. And the expected value of each of those xi's is itself mu. So we get the summation I equal 1 to n of mu. We get mu added up n times then, which is n mu, divided by n on the outside. So we get mu. So what this says is it doesn't matter what the distribution of the individual x's is, the distribution of the mean of the x's has the same mean as the individual means. So let me just summarize one more time. The expected value of the sample mean is the population mean that it's trying to estimate. The population mean of the distribution of the sample mean of n observations is exactly the population mean that it's trying to estimate. And so when this happens, when the expected value of an estimator is what it's trying to estimate, that's a good thing. We say that the estimator is itself unbiased. So sample means are unbiased estimators of population means. And again, there were some assumptions for this to be true, right? All the x's have to be from a distribution that has mean mu being the value you want to estimate. And then the sample mean is an unbiased estimator of the population mean. And we're finally getting to the point where we can talk about how we're going to connect our probability modeling to the data that we observe. We're not quite there yet, but we're getting closer and closer to this. And I want you to remember that we're throwing around the term mean a lot. And so if you get confused, I want you to remember to qualify the mean that you're talking about, whether it's a population quantity, i.e. component of the probability distribution, or a sample quantity, an empirical quantity that you connect from the data. And remember, our goal in probability modeling is to connect our sample observations to the population using our probability model. So the variance of a random variable is another expected value property of a distribution. Recall the mean measured the center of a distribution. The variance measures how spread out it is. So if x is a random variable and it has mean mu, i.e. expected value of x equals mu, then the variance of x is defined as the expected value of quantity x minus mu, whole thing squared, and the expected value. So what does that mean? So the expected value is in essence an average, right? So it's sort of the average or the typical value that the random variable takes. It's the center of the distribution. On the other hand, the variance is sort of the average distance the random variable is from the mean. What that implies is that random variables with higher variances come from distributions that are more spread out than ones that have a lower variance. Let me just remind you what this formula, the variance formula, means again. If you were to take the random variable x and figure out what the distribution was if you were to subtract off its population mean, which turns out to be the exact same distribution, just with all the possible values of x shifted by the value mu, and then it has mean 0. And then I were to take that random variable and figure out what the distribution of the square of it is, then take the expected value of the resulting random variable. And that's hard. So we don't ever calculate the variance that way. We typically calculate the variance by a convenient shortcut. And that is that the variance of a random variable is the expected value of x squared minus expected value of x quantity squared. And again, this expected value of x quantity squared is just mu squared. This shortcut formula then requires you to calculate the expected value of x squared. But again, the kind of typically the more convenient way to do that is to use, if it's discrete, the summation of say t squared p of t, where p is the probability mass function, or if it's continuous, use integral t squared f of t, where f is the density function. It would be nice for you as an exercise to show that this original variance calculation equals this shortcut variance calculation just by expanding the square and using the expected value rules. It would be convenient if the variance operator was also linear. It's not. As an example, the variance, if you pull a random variable out of the variance, it gets squared. So variance of a times x, where a is not a random variable, is a squared variance of x. The square root of a random variable is called the standard deviation. And the reason we use standard deviation often instead of the variance is that the standard deviation has the same units as the random variable. So let's say x as a random variable has units in inches. The variance has units inches squared, whereas the standard deviation has units inches. So it's often quite convenient to talk about the spread in the same units as the random variable itself. So the standard deviation is a very common summary of the variance. Well, let's calculate a sample variance. What's the sample variance from a toss of a die? So in this case, expected value of x is 3.5. We've covered that already. And expected value of x squared, let's calculate that. Well, we have 1 squared times a sixth plus 2 squared times a sixth plus 3 squared times a sixth plus 4 squared times a sixth plus 5 squared times a sixth plus 6 squared times a sixth. That works out to be 15.17. And then you subtract 15.17 minus 3.5 squared, and that works out to be about 2.92. Let's go through a very important formula. Let's suppose we flip a coin, but let's make it slightly more interesting. Instead of the coin having probability 1/2 of a head, let's say that it has probability p of a head. So here, expected value of x equals 0 times the probability of a tail, which is 1 minus p, plus 1 times the probability of a head, which is p. So it works out to be p as the expected value. And of course, this agrees with our calculation when the p happens to be 1/2 for a fair coin. Now let's calculate the expected value of x squared. Well, actually, it's kind of interesting in this case. It's pretty easy to do that, because x takes only the values 0 and 1. And if you square 0, you get 0. And if you square 1, you get 1. So x squared is in fact exactly x. So expected value of x squared is equal to the expected value of x, which we already calculated is p. So the variance of x in this case is expected value of x squared minus expected value of x quantity squared, which is p minus p squared, which works out to be p times 1 minus p, which is a formula you may have encountered before. It's interesting to note that this variance formula is maximized when p is 0.5. So just simply plot the function p times 1 minus p between 0 and 1. So plot this function between 0 and 1, and you'll see that it maximizes at 0.5. So the most variable coin flip can be is, in fact, exactly a fair coin. It's interesting to note that the most variable a random variable can be in general is if you shove all its mass to two endpoints and equally distribute it between those two endpoints. So if you have a continuous random variable and you want to make it more variable, kind of chop out the middle and spread it out equally distributed between the two ends. And in fact, let's talk about this in greater detail. Suppose that you have any random variable, like a uniform random variable, that's between 0 and 1, and its expected value is p. Now, since the variable takes values between 0 and 1, p has to be a number between 0 and 1. And then notice if x is a random variable that's between 0 and 1, x squared has to be less than or equal to x. Because if you take any number between 0 and 1 and square it, you get a smaller number. And so expected value x squared has to be less than or equal to expected value of x, which is p. Therefore, the variance of x, which is expected value of x squared minus expected value of x quantity squared, has to be less than or equal to the expected value of x minus the expected value of x squared, which is p times 1 minus p. And basically, this is then just a proof that the Bernoulli variance, this binary variance where the random variable can only take the value 0 or 1, is the largest possible for a random variable that has expected value of p. And then we also noted that earlier that the maximum value that you can get is when p is in fact 0.5. So this basically just shows that this is basically a simple little proof that the random variable, that the largest variance that you can get for a random variable is that you sort of shove its mass to two endpoints, and the closer you can get to an equal mass in both the endpoints, the larger the variance is. I'm not sure if I've mentioned this previously, but I called the variable a coin flip that can take heads with probability p. I called it a Bernoulli random variable. This is named after the mathematician Jacob Bernoulli, who is one of the fathers of probability. And Jacob Bernoulli is an interesting character. You should read up on him. The Bernoullis were a very famous mathematical family. They came up with lots of discoveries. Jacob was a particularly influential member of the Bernoulli family, and he discovered quite a bit of probability theory very, very early on. At any rate, when you have a random variable that takes the value 0 or 1 with probability p, then we call that a Bernoulli random variable. So here we are back talking about variances, and variances are kind of difficult things to understand, and equivalently standard deviations. I prefer to interpret standard deviations. Intuitively, we know that bigger variances mean distributions are more spread out, but we need some way to actually interpret what bigger means. Now, in the context of a specific distribution, we might learn the kind of quantities associated with that distribution to know that, well, what does one variance mean, or two standard deviations mean, three standard deviations mean? And that's particularly true of the Gaussian or bell-shaped density. We tend to know the values associated with those variances sort of by heart. But there is a general rule that applies to all distributions, and it's so-called Chebyshev's inequality after the Russian mathematician Chebyshev. So at any rate, Chebyshev gives a really useful inequality for interpreting variances. So basically, the inequality says the probability that a random variable is k standard deviations from its mean or more is less than or equal to 1 over k squared. So let me repeat that because it's so important. The probability that a random variable is more than k standard deviations from its mean is less than or equal to 1 over k squared. And let's just look at some simple benchmarks for k. The probability that a random variable is more than 2 standard deviations from its mean is 25% or less. The probability of the random variable is 3 standard deviations from its mean is 11% or less, and the probability of the random variable is 4 standard deviations from its mean is 6% or less. And again, note that this is a bound on the probability statement. It's not an equality. So it's the worst that it could possibly be. The lots of distributions, the probability of being 4 standard deviations or more beyond the mean is far lower than 6%, but 6% is the worst it can be. So it's unlikely, say, for example, that you will, if you observe a random variable, it's unlikely that you will see that random variable be, say, 6 standard deviations from the mean. That's quite unlikely. That's has probability less than 1 over 36, regardless of the distribution. What's interesting about Chebyshev's inequality is that it's quite easy to prove. And so let's just go through the proof really quickly. Well, let's look at this probability statement. The probability that a random variable is more than k standard deviations from its mean. And let's do it in the continuous case. Let's just do it in the continuous case. You can prove it more generally, but this just gives you the intuition behind the proof. Well, that's the integral over the set of x where it's more than k standard deviations from the mean. Where here now the little x in the domain of integration is a dummy variable of integration, f of x dx, and this could be, we could replace this by another letter over on the right-hand side, but on the left-hand side it has to be capital X. Well, notice that x minus mu over k sigma, absolute value x minus mu over k sigma, has to be bigger than 1. So if we square that, it has to be bigger than 1 as well. So if you take a number that's bigger than 1 and square it, it's still bigger than 1. So we can multiply by x minus mu squared over k squared sigma squared, and we've only made the integral bigger, right? So we can replace this equality with an inequality where here the alligator's chomping the bigger part. Okay, so now we have this quantity here, and we'll only make it bigger yet if we, instead of integrating over this restriction of the domain, we integrate over the whole thing from minus infinity to plus infinity, because everything, the x minus mu squared is strictly positive, so we'll only make it bigger. And then notice now that the k squared sigma part is a scalar that we can just factor out, and then we have minus infinity to plus infinity x minus mu squared minus infinity to plus infinity integral of x minus mu squared f of x dx. Well, that's just exactly the definition of the variance. And so that equals sigma squared. The sigma squareds cancel and you get 1 over k squared. So we see that the probability that x is more than k standard deviations from the mean, we started out with an equal sign, we got bigger, then we've had a final equality, so the whole thing is less than or equal to 1 over k squared. So I find it remarkable that Chebyshev's inequality, this powerful result that applies to all distributions, has such a simple little proof. Let's go through some numerical examples just to show why this result is useful. So intelligence quotients, and I would recommend that you look up intelligence quotients. Are often called Binet scales. They have a very rich and interesting history that intersects with statistics and several other fields in psychology and so on. It's really quite an interesting literature on intelligence quotient. So I would highly recommend you look it up just because it's quite fun. But let's kind of skirt that discussion and just say, let's suppose intelligence quotients really are distributed with a mean of 100 and a standard deviation of 15. What's the probability that a randomly drawn person from this population of people that have IQs with mean 100 and standard deviation of 15, what's the probability of drawing a person with an IQ higher than 160 or below 40? And of course, I picked the 160 or 40 specifically. Well, 160 is 4 standard deviations above the mean, and 40 is 4 standard deviations below the mean. So Chebyshev's inequality that this will be no larger than 6%. If in fact the IQ distribution is bell-shaped or is Gaussian, this bound is very, very conservative. Just to give you a sense of how conservative, the probability that a random draw from a bell curve being 4 standard deviations from the mean is not 6%, but on the order of 10 to the minus fifth, 1,000th of 1%, which again, it doesn't violate Chebyshev's inequality. 10 to the minus fifth is less than 0.06, so it's fine, but it's quite a bit less. So just to give you a sense of how conservative Chebyshev's inequality can be. Let me go through another example. So a buzz phrase in industrial quality control is Motorola's so-called Six Sigma. And I have to admit to being largely ignorant of exactly what the Six Sigma industrial protocol is. But the gist of it, as far as I understand, is that businesses are suggested to control extreme events or rare defective parts. And the idea is that you go out 6 standard deviations. So let's, as an intellectual exercise, maybe you on your own can go look up what exactly the Six Sigma protocol is. Let's, on it as an intellectual exercise, talk about what the probability of 6 sigma events are. The idea of having a random variable that lies 6 standard deviations above the mean. Well, that's by Chebyshev's inequality, 6 standard deviations above or below the mean. By Chebyshev's inequality, that's the probability of such an occurrence is less than 1 over 6 squared, which is about 3%. So it's highly unlikely. But again, remember, Chebyshev's is a bound that applies to all distributions. If you know something about the distribution, for example, if you know the distribution is a bell curve, then the probability of a 6 sigma event is on the order of 10 to the minus ninth, which is, I calculated as 1/10,000,000th of a percent. So again, that doesn't violate Chebyshev's inequality. 10 to the ninth is less than 0.03, so it doesn't violate Chebyshev's inequality. But anyway, that's what a 6 sigma event is discussing.